Okay, here's the solution to homework number 7 for ECE 320. The first problem is a DC to AC converter. I've got 24 volts DC. I want to convert to 60 hertz AC. So that's what this circuit does. Kind of the way it works is when Q2 turns on, current flows up. When Q1 turns on, current flows down. So if I alternate Q2, Q1, Q2, Q1, what I get is current going up and down. That goes through the transformer and provides an AC signal to L1. What the capacitor does is acts kind of like a filter that you're trying to set up a resonant circuit between C1 and L1 so that I filter out the harmonics and I get a sine wave out. If I try 10 microfarads and 100 millihenries, this is where Circuit Lab is really nice. I can throw this into Circuit Lab, do a time domain simulation. VA, the orange line, is the voltage at Q2. VB is just not that. So when switching between the current going up, down, the capacitor plus the inductor doesn't quite work. Doesn't give you a 60 hertz signal. The problem is the capacitor and inductor apparently have a resonance at about 3 times 60 hertz, 180 hertz, which is what you're seeing. If you want to calculate what the capacitor should be, the resonance of an LC tank is 1 over the square root of L times C. For 377 radians per second, L is 0.1 Henry, C should be 70 microfarads. That doesn't quite work, so adjusting it, just trial and error, I got about 120 microfarads, gives you this signal. Notice that the blue line, that's the voltage at the inductor, is almost a sine wave. What that means is that it does have harmonics. It's not a pure sine wave, but the harmonics are very, very small, making this a highly efficient DC to AC converter. Almost all the energy is in the first harmonic. So this is just another circuit that converts DC to AC. There's a lot of them. Here's one of them. Problem 3. This is an AC to DC converter. So what I have is I've got 3 diodes. What you wind up with is, this is diode, well, let's just call this diode 1, 2, 3, 4, and 5. If these are just regular diodes, what happens is when the input, let's try the input in yellow, is a sine wave like this. What happens is diode 1 and 4 turn on for the positive half. Then 2 and 3 turn on as a rectified signal. Then 1 and 4, 2 and 3, 1 and 4, 2 and 3, they alternate. With semiconductor relays, what I can do is instead of turning on a 0 degree crossing, let's go back to I lost my signal. If this is your 20 volt input, and here's your 0 crossing, I can fire at some angle, like 45 degrees. So this is 45 degrees. What's going to happen is initially neither diode is turned on. That's when the diode 5 turns on. When diode 1 turns on at 45 degrees, suddenly I follow it. Once the voltage goes to 0, diode 1 turns off, 3 is still turned off, 5 turns back on. So this would be diode 5, this is 1. Now diode 2 and 3 turn on. That's a rectified signal. Looking kind of like this, turns off. So I get that kind of waveform. This firing angle I can vary between 0 degrees and 180 degrees, which basically varies the on-time, off-time. Diode 5 just says that when both diodes are turned off, I get minus 0.7 volts at V1. So, to analyze the circuit, I first want to find the DC voltage at V1 and the DC and AC voltage at V1 and V2. Starting at DC, the DC voltage at V1, equation in the lecture notes, is this is the average of a sine wave that's turned off at 45 degrees. Gives you 9.787 volts. That's the DC voltage at V1. Then at V2, by voltage division, it's 50 over 50 plus 5 times V1, 8.79 volts at DC. That's V2. To find the AC voltage. Again, the AC voltage, kind of what we're doing in class, is approximating this as a sine wave, the peak-to-peak voltage. The peak is 20, minus 1 to minus 1.4 volts, because there's always two diodes turned on at any given time, 18.6 volts, that's the peak. The minimum is minus 0.7, the difference is 19.3. So V1 is 19.3 volts peak to peak. The frequency is 120 hertz, so that's a full wave rectifier. Find the inductance at 120 hertz, J226 ohms, capacitance at 120 hertz, minus J26 ohms. Put the capacitor resistor in parallel, do voltage division. I get the voltage at V2, 2.19 volts peak to peak. If I throw this into problem 5, that matches up. The DC voltage I calculated was 8.79. We got 8.76, pretty close. The AC voltage, 2.19 volts peak to peak. Simulated in problem 5, 2.36 volts peak to peak. So the calculations seem about right. It won't be exact because V2 right here, this is not a sine wave, so the first harmonic is not exactly 19.3 volts peak to peak. We're doing approximations. Likewise, what I calculate for V2 will be approximate. It's not too bad. Kind of my book is, if you want to get more accurate than these approximations, throw it in Circuit Lab. Problem 4. This is design. Design so I have 10 volts DC and half a volt peak-to-peak ripple. In that case, what I need to do is, I know the DC voltage at V2 is 10 volts. By voltage division, V2 is less than V1, V1 is bigger than V2, V1's got to be 11 volts. That makes V2 equal to 10 volts. From this equation, I know that V2 is 11 volts. Find the firing angle, I get 25.25 degrees. AC analysis. I know I want to find C. So let's assume C isn't there. On this circuit, where'd it go? Oh, there it is. Assume C isn't there. Find V2 without C. So what I get is, it's the 50 ohms, get no capacitor, over the total. 50, 5 plus J226 times the input, I get 4 volts peak to peak for V2. The purpose of the capacitor is to reduce the impedance of the load at 1 kilohertz. I want the ripple to be 8 times smaller. I'm going down here, 8 times smaller. So I want the capacitor to be 8 times smaller than 50 ohms, 6 ohms. Pick the capacitor to be 6 ohms at 1 kilohertz, so that's 220 microfarads. And if you simulate it, I'll get something fairly close. To simulate it, that's problem 5. Write the differential equations that describe this circuit. Again, how I generate V1, the circuit doesn't care. Once I have V1, I can find the current I3 and the voltage V2. The basic equation for a capacitor is I equals C dV dt. So I2, I can find I2, I know the derivative of V2. I2 is just this current in minus current out. That's I3 minus V2 over 50. That gives you I2, which is C dV dt. The voltage V3, let's do that in orange. The voltage V3 right here is the voltage on the left, which is V1. The voltage over here is V2 plus I times R, plus 5 times I3. So I now have my differential equations that describe the circuit. Plugging in C and L gives you what? No, gives you this equation. For the input, this is a sine wave. The firing angle is 45 degrees. So I'm going to have time going between 0 and 1, because 0 to 1 is kind of nice. Angle is T0 times 180. If the angle is more than the firing angle, it's V0. If it's less than the firing angle, it's minus 0.7, which gives you, here's your sine wave. At 45 degrees, I turn on, and below that, I'm at minus 0.7. V0 is the sine wave 20 volt peak minus 2 diodes, minus 1.4. Clipped at minus 0.7, you can't go below minus 0.7. Once they get V0, that's the voltage on the left, on the circuit called V1, I want to take that voltage and apply it to this differential equation. So I'm going to go through the time vector, iterating, moving forward every dt seconds, go through a cycle. I'm going to go through 100 cycles because you're going to have a starting transient. It's going to do something kind of like this. After 100 cycles, you're probably at steady state. So after 100 cycles, I'll run. And what it looks like are the figures that we had before. Okay, come on. Which were this guy for problem 3, this one for problem 2. Last two problems. Implement this logic using NAND gates. With NAND gates, you circle the ones. So a couple ways to do that. I can circle this group of ones. I want to do powers of 2. That gives me this one right here. That's C bar D bar. The next one would be the red ones right here. That's A, D. The next one is these. That's A bar, D bar. It's getting kind of messy. And the last one would be the purple ones. That is B bar, C, D. Once I get the logic, I can implement that. This is going to be C bar, D bar, ANDed with C bar, D bar, or AD, or A bar, D bar, or B bar, CD. Once you draw that using ands and ors, I then throw in a double negative. So like here's the negative, double negative, there's a double negative, double negative, double negative. And not becomes NAND, not and, or not or, is also NAND. So this is how you implement it with NAND gates. For NAND gates, you circle the ones. To implement using NOR gates, I circle the zeros. If I do that, I get, like the red circle is A bar, C bar, D, first term. The purple one is A bar, B, D. And the blue one is A, C, D bar. I circle the zeros, so that's actually Y bar, or not Y. Now use De Morgan's theorem. Not Y is Y. And becomes or, A becomes A bar, so I get this. To implement that, I will take A, C, and D bar, or them together, A, B bar, D bar, or them together, A bar, C bar, D, or them together, and the three outputs, I get Y. Now throw in the double negatives. So here's the double negative, here's the double negative, here's the double negative. Or not is NOR, not and is also NOR. So to implement a gate using NOR gates, circle the zeros. To implement it using NAND gates, circle the ones. And that is this homework set.